this video, I will talk about a very interesting article from FinTech magazine about the importance of quantum computing in the banking sector. And we will talk about a very interesting exercise about the quantum efficient frontier. Let's start with the article called How Quantum Computing Could Transform the Banking Sector, where the article mentions that quantum computing is an emergency technology often overlooked in favor of en vogue innovations like artificial intelligence and cloud. How might quantum banking change the financial system? Quantum banking is perhaps one of the last champion trends within financial services today, yet it still has the potential to have a significant impact on the financial system. One of the most considerable advantages that quantum banking provides over alternative methods of banking and moving money is the increased speed. Quantum computing can process data 10 million times faster even than the supercomputers, highlighting the astounding capacity that this emergency technology possesses. The authors of a IBM report into quantum banking explain the technical advantage. The solution space of a quantum computers is order of magnitude larger than traditional computers, even immensely powerful ones. That is because doubling the power of a classical computer requires about double number of transistors working on a problem. The power of a quantum computer can be approximately double each time only one qubit is added. This system in turn provides powerful advantage to financial institutions and other players with the banking space, and it's not going unnoticed by the industry. A recent report published by Tememos surveyed 300 executives across retail, commercial, and private banking around the world says that 60% of executives through new technologies, including quantum computing, will have the biggest impact on bank in the next 5 years. The article also talk about the risk management among other quantum use cases. Another significant use case for quantum banking lies around risk, which continue to be an operational tug of war for banks of all sizes. Quantum computing can perform operation magnitudes quicker, meaning complex financial information, such as the data that goes into assessing credit risk, for example, can be analyzed quickly and with more accuracy. A study published earlier and in this year by Ernst & Young highlights the complex risk landscape that banks are operating in. It claims that CROs face an extraordinary volume and variety of risk, both traditional and emerging, which all seems to be growing in urgency. This is terrible. Yet their biggest challenge lies in understanding how this risk intersects with each other to create potential points of failure with their organization. Even when traditional risk management metrics appear or look stable. Cyber risk is a top risk priority for the next 12 months, according to the CROs in this study. But credit risk may soon become more of a focal point in economic condition worsen. Clearly, then, this necessitates improved technology to help financial institutions manage the plethora of risk they face on a daily basis. Could quantum banking be a solution? Well, in Fermat risk. However, the first mover will secure an early advantage. Authors of a report from UK Finance previously wrote, quantum computing will have application across financial services, transforming the way we approach investment, risk, artificial intelligence, security, and offering financial services firms the opportunities and early advantage. financial services firms should be considering how they prepare for the quantum computing technology that looks certain to transform the market. Failing to do so risk other developing the ability to move faster in the short term and to attract the resources that will be essential for long-term success. Okay, now let's talk about an application of quantum computing and quantum annealing in the famous efficient frontier used in investment portfolios, where we'll see a very interesting exercise in Jupyter Notebook and Python. An efficient frontier is a set of investment portfolios that are expected to provide the highest return at a given level of risk. A portfolio is said to be efficient if there is no other portfolio that offers higher return for a lower or equal amount of risk. Okay, we will use an impressive library or package in Python named PyGRND, and we will see more detail about this package. First, we talk about the technique in quantum computing that we will use is the quadratic and constraint binary optimization in QO. QO is part of problems of NP-hard. NP-hard is non-deterministic polynomial time harness combinatorial optimization problems which can be solved by quantum annealers and various classical algorithms. Although having a constraint in its name, we can actually implement linear constraints into QOs by adding penalty matrices to the original QO metrics. Grover et al. Give a comprehensive introduction to this topic. Okay, the idea of this quadratic optimization is use the variables w sub I when I belong to 1 to n and satisfy that w I belong to 0, 1, and we can approximate each w subindex I by its binary representation so that the problem can be encoded as a QO, and this uses the same idea as in Palmer et al. Okay, and we don't go into details here in this notebook. The notebook will focus on solving multi-criteria quadratic optimization problems using precisely QO approach. QO constitutes a central problem class from adiabatic quantum computation where it's solved through a physical process called quantum annealing. Okay, adiabatic quantum computation use a concept very important named Hamiltonian. Hamiltonian is a system, is an operator corresponding to the total energy of the system. And this energy divided into one is kinetic energy and potential energy. Kinetic energy is when an object is a form of energy that it possesses due to its motion. And potential energy is the energy held by an object because of its position relative to other objects stressed with itself, its electric charge, or other factors. Okay, its spectrum, the system energy spectrum, or its set of energy eigenvalues, is the set of possible outcomes obtainable from a measurement of the system total energy. Due to its close relation to the energy spectrum and time evolution of a system, it's of fundamental importance in most formulation of the quantum theory. Now, quantum adiabatic computing is a quantum computing paradigm alternative to quantum circuits, where the initial state is slowly evolved with a time-dependent Hamiltonian to a final state. It's based on the adiabatic theorem, which guarantees that if the evolution is slow and the energy level do not cross, the fundamental state of the initial Hamiltonian will evolve to the fundamental state of the final Hamiltonian after a sufficient long time. Adiabatic computation is useful for attacking problems where the fundamental state of the final Hamiltonian encapsulated the solution to a problem, for example, a minimization problem that we will use as you can see more later. Quantum annealing is an optimization process for finding the global minimum of a given objective function over a given set of candidate solutions by a process using quantum fluctuations. And quantum annealing is used mainly for problems where the search space is discrete with many local minima. Okay, in 2011, the D-Wave system announced the first commercial quantum annealer on the market by the name D-Wave 1 and published a paper in Nature, this very prestigious magazine of papers, of scientist papers on its performance. The company claims these systems use 128 qubits processor chipset. Actually, I think that have approximately 5,000 qubit processor chipset. D-Wave architectures differs from traditional quantum computers. It's important to say this. It is not known to be polynomial equivalent to a universal quantum computer, and in particular cannot execute, for example, the Shor's algorithms, because Shor algorithms is not a hill-climbing process. Shor algorithms require a universal quantum computer, for example, like a IBM computer that have not more than 500 qubits. It is the difference with these D-Wave architectures is use precisely the quantum annealing optimization. Okay, now the asset allocation and multi-criteria optimization. The asset allocation is a problem, and more late we will see the multi-criteria optimization. Okay, in the asset allocation, according to Markowitz' modern portfolio theory, exists n number of assets, and each asset is numbered from I belong to 1 to n, and can be treated as a random variable x I, and its respect return mu sub I and standard deviation sigma sub I, and can be estimated with historical stock data. For every two classes, I, comma, J belong to 1 to n, we can estimate their correlation rho I, comma, J belong to 0, 1, where the covariance of the two assets is calculated like a sigma sub I, comma, J equal to sigma of I times sigma sub J times rho I, comma, J, and the covariance matrix is defined as sigma. In the case of the I equal to J, the value simply is sigma square sub I, is the variance of an asset I. Okay, assume that the available amount of capital is large enough so that the stock price of each asset doesn't matter, and the capital can be distributed in each asset in continuous percentage. In case a portfolio can be encoded as a vector of weights, and the weights, the vector weight equal to W sub 1 to W sub n transposed belong to 0, comma 1 power set n, with the sum of the weights, that the sum of the weights could be or need to be equal 1. The portfolio W produce a random variable, and this random variable x sub W is equal to the sum from I equal 1 to n W sub I times x sub I, no? With expected return and variance. As we can see, the expected value of this x variable is equal to mu, as you can see here, transposed times W vector. And the variance of this, the result is W transposed times sigma, I mean the covariance, times W. This part is the return of portfolio return, and this is the risk of the portfolio, or portfolio risk, and its volatility that given as the square root of the variance. Okay, the goal of this model is to find a portfolio with a maximized return and minimize volatility. And for obtain this, we can have we have in this model with the maximum B mu transpose times W, and the minimum is exactly the portfolio risk. Okay, subject that the sum of each element of the vector weight need to be equal to 1, or this is, and this condition W belong to 0, comma 1 power set n, means that each element of W need to be positive. This is the objective too in this. Okay, and with this linear constraint that the sum of weight need to be equal to 1 ensures that the total budget of 1 equal to 100% holds, and the range constraint is basically to the weights, all the weights must be positive. I mean only long positions and not a short sale position. I mean we can't ask, for example, a loan to invest in this and have a short sale or negative position, and each of them should not be exceed to 1%. Okay, the two objectives are generally conflicting for optimization problem with multiple objectives. It is typically not possible to search for the optimal solution, just because for one side we are looking maximize the return, and for other we are looking minimize the risk. Okay, then in case of a portfolio optimization, the solution set is the called efficient frontier. However, we can use multi-criteria optimization algorithms, and this kind of models consider a problem where the vector that we have W transposed is the vector of variables. I mean the weights, and we have these models where we can have a lot of minimization functions as we can see. For example, f sub 1 w to f sub a w. Okay, subject to g1 w equal to 0 to g sub b w equal to 0, and the condition to be positive. Okay, we only considering minimizing the objectives because maximizing a function f can be achieved just minimizing the minus f. I mean, minus f is equivalent to maximize. Okay, f. Below are some often used methods for solving the multi-criteria optimization problem above. One is scalarization, turn multiple objectives into one, and the objective functions and the approach are weighted sum method. These add up the objectives with different scaling factors and use lambda sub k below. Then optimize the combined objective in order to find the efficient frontier. And we can solve different instances of, as we can see here, minimizing the sum from k equal 1 to a lambda sub k f sub k w, and subject to this function g sub l w equal 0 and the condition of b positive that I told before, and for all L belong to 1 to B. In case of asset allocation, if we impose the budget of 100% as penalty term to the objective functions, then it's the same idea as minimizing what? Look at this, the return portfolio, okay, the risk portfolio times gamma over 2 plus rho, and the condition of the sum of the weights could be equal 1. Okay, for some two variables is gamma and rho greater than 0. A formula often seen in related papers about this. Okay, there are other approach. This approach we can see, and this, yes, we can show is the Monte Carlo method, is the trial and error. Instead of using an optimizer algorithm, we can generate a large number of samples, solution candidates. Every W need to be positive. Then we calculate all of function f sub k w and g sub l w for each w and filter out the better samples. In case of the asset allocation, we generate 1 million random portfolios, calculate their expected return and volatility, and find out the best portfolios based on the information. Okay, the use of this amazing package named by GRND is amazing because solving quadratic optimization problems, and this is the kind of solution that the models that we will see in this package. We can minimize or maximize, okay, this equation that you can see that this is in our case the portfolio risk. A could be, for example, the matrix, the covariance matrix, and in this sense, for example, B could be, for example, the mu, the returns of the portfolio, plus C, that C could be a constant. Okay, and we have then a lot of problems to resolve subject to these constraints, and the constraints here are focused in the transposed sub 1 times W plus E. E sub 1 to E sub B, like you can see here. And with the condition too that every one W need to be positive, where W is a vector obviously of variables. I mean the weights that we need to solve. A are real valued matrices, okay, maybe the covariance or other metrics that we have. B and D are the real valued vectors, and C and E are real constants. Okay, then we will see an illustrated example, and after we will see a real example. Okay, this is an example of 5 assets, and in this case, okay, there are a little program to estimate between, also using random values to obtain mu. Mu is the expected returns of the assets, and the standard deviation, the correlation, and the covariance. And we can see this beautiful graph that or figure that show the vector of mu, the vector of sigma, correlation metrics with different colors. More red means more close to 1, and more blue means are negative, close to -1, and this is the covariance metrics. Okay, now we want to solve, in this example now, just these two objectives. For one side is maximize the return of the portfolio, and minimize the risk portfolio. And this subject to the sum of the weights equal 1, and the other condition is the weight be positive. Okay, now it is very interesting because have then two objectives, one constraint, and using the notations above, we have then that we can have kth objectives, minimum and maximum with this expression, and L constraint. And in this sense, the objective 1 is maximize, as we can see. A don't need to use, for this is 0, but we have this expression. For the reason B is equal to mu, and C don't use because we don't have constant in this expression, and just is the value equal 0. Now the second function, okay, is the risk, and the risk half A, like this expression is equal to sigma, but we don't have B expression and C. In this sense, B and C are equal 0. Okay, and now the last restriction, when the sum of the weights equal 1, we use, in this sense, from D, this vector of 1's transposed, and the term, yes, is a constant. E is equal to -1. Okay, and now express this is very easy in this program, in this code, because we can see the objects are then the maximum, okay, 0 mu 0 comma mu comma 0, and the minimum is just sigma comma 0 comma 0. Absolutely easy. And the constraints is equal, okay, because it's now the value that we need, and the sum of n and the constant is -1. Okay, we can use a Cubo resolution that returns two lists of matrices for the given objectives and constraints with the number of binary resolution bits specified as parameter m. And m for default takes the value of equal 6. However, in this sense, just use m equal 4. More later, I will explain about the significance of this m equal 4. Okay, then we apply this and this Cubo resolution, and the next step is plot, for example, here the matrices that we have. The first is the objective to reduce or minimize the risk. Okay, and we can see here the areas of the matrix that show the two colors. Red color is more positive and blue colors are negative. Here the objective of the return, the portfolio return, and you can see the diagonal, and here the covariance with colors, and here the constraint to produce weights equal 1. Okay, solve Cubo solve an input problem with the weighted sum approach. And for this problem, if we input scaling factors lambda sub 1 and lambda sub 2 and penalty factor p sub 1, it minimizes this expression, as we can see. No? The first part is return portfolio, the risk portfolio, times lambda sub 1 and lambda sub 2 respectively, plus p sub 1 for this expression is weights need to be 1. Either with the wave system quantum annealing hardware or with simulated annealing algorithm. What means this? Okay, this package have two options. One is use directly the quantum annealing hardware of the wave system. In order to do this, you need to obtain a token in the page, register. It works for specific countries. And the other, if you don't have the token, then the software use a simulated annealing algorithm. In this sense, we don't use really a quantum annealing hardware. Okay. Now the solve Cubo have other parameter named disp, and it decides whether the solution details should be displayed, and the m test parameter determines the number of testing runs, and the default is 1. Okay, and the solve Cubo have then these instructions. Lambda are the scaling factors. P in this case is the value, the penalty factor that in theory looking for minimize this expression. As you can see, m equal 4 produce these results. The results with the combination, okay, of zeros and 1 with 4 positions, and this display is true, and we can obtain then the weights, the optimal weights that found using these two objectives. The first objective is the objective 0 is related to the return with the portfolio of 13.8%, and the other is the risk that have. Okay, using this 0.8 5 or 0.5 of the values of lambda. Okay, solve cubo CSO also solved with the weighted sum approach, but it used the classical optimization algorithm from SciPy Optimize. And this method only need the scaling factors lambda sub 1 and lambda sub 2 of the objectives. And it is not needed to specify the penalty factor p sub 1 as in solve Q. But one can specify a starting vector w 0 of the optimization process. Okay, then the code is put in this case. Don't need m as before. We estimate. M equal 4 and penalty don't use because it use just the SciPy optimize, o sea, the traditional optimization, not quantum. And the result, as we can see, is these values of weight is a little bigger than the optimization that we have in the Cubo, 13.8, and this is the no, sorry, I told but the objective one, yes, is the return, and it have more return the Cubo, yes, and the risk is very similar. Is a little is less this in the Cubo that the optimization of the SciPy. No? In other words, is better the result because we have the same risk, but it has a better return. The Cubo is better in this case. This is one of the benefits to use the Cubo. Now we need to compare not just with this traditional optimization, but using Monte Carlo 2. Okay, this package have a very interesting code and function named efficient frontier. Is absolutely good. Have two weighted sum scalarization. One is the method weighted sum, and weighted sum using the classical algorithms. The optimization by SciPy. And the other is absolutely interesting because it's the weighted sum annealing that use the D-wave package, okay, by using a solve Cubo. However, here, as I told, if we use the DW token, okay, we can use directly the D-wave quantum annealer hardware, okay, and it's obviously is very powerful. Need to stay in a queue and maybe delay for the reason, but in theory is could be more fast because we are really using quantum hardware. No? Quantum annealer is important because it's different to the universal quantum computer. Okay, and depend to the W token, also obtain the DW token, their region. Is important to say this. Okay, if we don't have a token, then just use the wave package using simulated annealing algorithm. Okay, the other efficient frontier method is the Monte Carlo. Monte Carlo, pues just make a Monte Carlo simulation. And we have here the code. The first code is to the weighted sum, is using the SciPy optimize a classical algorithm, and this is the weighted sum annealing, okay, and this is the Monte Carlo, just use 1000 simulation, and the time obviously is absolutely bigger the simulation of Monte Carlo than the weighted sum annealing, okay, or simulated annealing. And in this sense, the results we can see, this is the efficient frontier. In the vertical axis, we have the returns, and in the horizontal axis, we have the risk, okay? And this is the classical frontier efficient using the traditional algorithms. This is the simulated annealing, okay? And this is the Monte Carlo. In theory, and in the practice too, the simulated annealing, if we put in a same graph, the simulated annealing in theory could obtain better results related to risk and return over the Monte Carlo. This is the theory in real portfolios, and for this reason have an advantage. The other advantage is are more fast than the Monte Carlo approach. Okay, here the token, don't put my token about this about the wave. Delay a little because the operation is in queue. It's important to say. And if we use then the token, the results change a little, have this process. This is the SciPy optimized, the classical efficient frontier. This is the simulated annealing, and this is the D-wave hardware. In theory too, the D-wave hardware should be better than simulated annealing. Okay, and this is the Monte Carlo that is used for a lot of asset managers, and is more slow than this simulated annealing that I am explaining. Okay, if we use other example, this example is of asset allocation with real data. This is a real data, and we have here mu that have the returns, sigma, the deviation, and have the correlation. Okay, and suppose that we use other metrics. For example, maybe behave similar to the covariance metrics. Maybe use other kind of problem that we can modelize or modeling, and we want additionally to minimize, for example. And this is now the square root of the W transposed times C times W. Okay, and in this sense, here we estimate the new metric C using other metrics S and doing this operation here. But it's other kind of metrics. Okay, and then we have here the correlation, for example, the covariance, mu and sigma in this case. I mean, it's not C here. No, here we can see C. This is the new metrics, other objective that we have. This is the constraint that weights could be equal to 1. This is the return portfolio, and this is the risk portfolio. Okay. And then, okay, in this sense, we have this problem more complex, obviously, because have the return, have the risk, and other metrics that we can to minimize. That is the metric C too. And then the code increase now because have the maximum 0, mu 0, the minimum sigma, and the minimum C2. Okay. Well, to do the Monte Carlo, first and do to have representative asset weights, each element of W sub I of the vector W is assigned to a value in 0 and 1 as follows. And we use this algorithm for 60% of the time. W sub I equals 0. For 20% of the time, W is calculated as a maximum of these variables that are uniforms, 0, 1, and are independent. And other 20% is calculated like a minimum, where these variables follow a uniform distribution with parameters 0, 1. And we have here the code that do this algorithm that I told. And here again, use the weighted sum, mean the classical algorithm, the weighted sum annealing, okay? Not use in this case the D-wave token and the Monte Carlo simulation. And we have the next results. Have the classical efficient frontier, this is a real case, the Monte Carlo, okay, and the simulated annealing. And simulated annealing is the best, is more quickly, absolutely more quickly in time over the Monte Carlo. And here we have other combinations of the variables, are more combination, for example, with the return, with the new metrics etc. Okay, in real world market circumstances, the pool of financial assets contains a wide range of assets from which we must select assets for our portfolio. As can be seen, many funds contain maybe more than 50 assets, and allowing additional flexibility in portfolio creation will result in a portfolio with a large number of decision variables to be optimized. For example, Standard & Poor's 500 index has just 500 assets, and if we have buckets of 1% for each asset allocation, we have 101 buckets for each asset, and in total we will have this quantity, 50,500 decision variables to be optimized for a high number of variable standard portfolio optimization solutions, such as Monte Carlo simulation may deliver lower performance because it's a lot of computational effort that we can do. Okay, and this solution using the solve cube now with m equal 6 that have all the combination of bits of 0, 1, and using the same percentage of lambda and the penalty equal 20 and display we have, and then the solution, and this is the optimal that we can obtain. I mean, this is the weights that we have, no? Then the above graph, this graph compares the portfolios built by Monte Carlo and the quantum optimization solutions. As per the results, quantum optimization deliver portfolios with better risk-return profiles than the Monte Carlo-based classical optimization solution, and the quantum optimization runtime is more fast than the Monte Carlo. I hope you like the video about the quantum efficient frontier. We have more advanced exercise in our course named Solvency II, Artificial Intelligence and Quantum Risk Modeling. The objective of this course is to show to the participant the requirements of the Solvency II directives, the recent IFRS 70 regulation, insurance contracts, as well as risk appetite and stress testing methodologies in insurance companies. The course proposes the use of artificial intelligence and quantum computing for the modeling economic capital, reserves, premiums, and claims, as well as for the optimization of portfolios and the management of the asset and liability in insurance companies, as we have seen in the exercise. I highly recommend this course to actuaries and risk professionals in insurance companies. We have received very good feedback over the last 15 years. And as you can see, we strive to offer solutions applicable to your work. The next video is from other economic sectors, such as the energy and the real estate. Expect it soon. Thank you very much.